Hi and welcome to a tutorial over electron configurations, Aufbau, Pauli, and Hund's rules. In this tutorial, we're really going to emphasize the electron cloud and kind of break it down for you so you get a better idea of what the electron cloud looks like. So it says electrons are found outside of the nucleus in a region of space called the electron cloud. To the top right, I have a little diagram, and as you can see, there's a little red dot. It's kind of just bouncing around everywhere. This is our electron, and it's more of a real-life example of what electrons do. They kind of just move around randomly. So we do our very best to predict where they actually would be located. Since electrons are organized in energy levels of positive integer value, it's the period number on the periodic table. So I have a periodic table for you to look at. And here are the period numbers. So if I say that an electron is in energy level 1, then I'm talking about in period 1 on the periodic table. Within each energy level are sublevels. They're designated by blocks labeled S, P, D, or F. So I'm going to go ahead and label this periodic table for you. All right, this first block, and we'll do this in class together, including helium, is called the S block. If you move over to the right, this one is called the P block. The one in the middle, which is basically your transition metals, is called your D block. And then the one at the bottom, this is your F block, made up of the lanthanide and the actinide series. Something important to note here is the energy level that these blocks start at. So I want you to memorize this early so you don't get confused. The S block starts at 1s, so energy level 1 in the S block. The P block starts at 2 energy level P. And then D block starts at 3D, which is kind of easy to memorize, right? 3D. And then F starts at 4F. Okay, so memorize that. It will help you so much later on. And then each sublevel corresponds to a certain electron cloud shape called an atomic orbital. I'll show you more of what that looks like later. So here's an analogy for you. The electron cloud is like Seven Lakes High School. The energy levels are like the floors in the school. The sublevels are like the teacher's rooms on the floor in the building. The orbitals are like the lab desks within a room, like my room. And the electrons are like the people sitting at the desks. So this gives us a good prediction of where electrons are by using these terms, energy levels, sublevels, orbitals. Okay, they give us a compartmentalization of the electron cloud. So what do atomic orbitals look like? Well, we've got S, P, D, and F, right? They're very complicated. So S is kind of spherical. P is like a figure 8. You don't need to know this really or memorize it. It's just adding to your knowledge so you have a better idea of the actual patterns they take. So it says, how are they organized around the nucleus? These atomic orbitals, they literally are the path the electron takes around the nucleus. They tell us where there's a high probability of finding an electron. And at the bottom, there's an example of the orbitals that make up the first 4 sublevels. So you can kind of see the S is in the middle, then on top of it you've got these figure 8s. So they just kind of build upon each other, making up this electron cloud. Each orbital can hold a maximum of 2 electrons. So if we look at the S sublevel, it is actually 2 elements wide. So that is why it is 1 orbital, because each orbital can only hold 2 electrons. So it asks how many total electrons can fit in the S sublevel. That would be 2. If we look at P, 1, 2, 3. It's made up of 3 p orbitals, but 1, 2, 3, 4, 5, 6 electrons can fit in there. If we look at D, it's much, much wider. This is actually 5 orbitals, so that's 10 electrons that can fit. And then we've got the F, which is the very longest. It has 7 orbitals, which can fit 14 electrons. So just like in my room where we have our desks, if my lab desk represents an orbital, I've got 2 people that sit there, right? So think of those desks as the orbitals and electrons as people. That'll kind of help you to remember. Okay, electron configuration and orbital diagrams. These are two things I want you to be able to do for me. They're methods used to represent the arrangement of electrons in an atom. So there's 3 rules: the Aufbau Principle, Pauli Exclusion Principle, and Hund's rule. We're going to learn about what those are. So the Aufbau Principle, it comes from the German verb aufbauen, which means to build up. So what does that mean exactly? The rule is that electrons enter orbitals of lowest energy first. Well, if we look at the periodic table, the lowest energy is right here, 1. The Aufbau order lists the orbitals from lowest to highest energy. So I know this looks like a mess to you right now, but we're going to learn to use our periodic table to get this order. You don't have to memorize that. It's too ugly. So it says, what do these letters and numbers mean? Okay, so when you see 1s2 or 3p6, what does that mean? Well, this first number right here, this is the energy level. Remember, that's the period on the periodic table. The P, that's the sublevel or the block it's in. And the exponent or superscript is the number of electrons fitting in that orbital, or sublevel rather. Okay, so if you see how they got this 1s2, it's because we start in 1s block and it's 2 wide. So that 2 becomes the exponent. And then you just go down on the periodic table to the second energy level. We're in the s block, so we would write 2s. It's 2 electrons wide, so you would write 2. So we get 1s2, 2s2. Now you want to go across and we run into 2p. Well, how wide is p? It's 6 electrons wide. That's where they get 2p6. When you go down, we run into 3s. It's 2 wide. You go across and you run into 3p. It's 6 wide. You go down, you hit 4s. It's 2 wide. So you can see where these exponents are coming from. Okay? And again, now when I go across, I'm going to hit this d block. It drops an energy level. Why? We don't really know, but it does. So it starts at 3D. So I know we've got 4s, but then it goes to 3D. Well, how wide is that? It's 10 electrons wide, so that's my exponent. And it just continues. And we use this to represent different atoms. So let me show you in a few minutes what an example of that is. So next, the Pauli exclusion principle. It says that an atomic orbital may hold at most 2 electrons, just like my desks. And they must have opposite spins called paired spins. So what does this look like? An orbital will usually draw as a dash or box. An electron will be represented by these arrows, and when they have opposite spins, you draw one up and one down. So here's your example of 2 electrons fitting in an orbital. And I'll show you these diagrams later. And then there's Hund's rule, which says when electrons occupy orbitals of equal energy, such as the 3p orbitals, 1 electron enters each orbital until all the orbitals contain 1 electron with parallel spins. So here's an example, okay? When it's 2p3, notice how we've entered the orbital singly. Okay, but if we go down and we go further, where it's like 2p5, you'll go 2p1, 2p2, 2p3, and then you go back 2p4, 2p5 to couple these. Again, I'll show you more examples later. So examples of electron configurations. So the electron configurations are written out in the Aufbau order. So my first example for you is going to be carbon. So the total number of electrons in carbon, we find it on the periodic table, is 6. So in our electron configuration, we need to write this out to represent those 6 electrons. So we start at the first energy level in 1s. Well, there's 2 electrons, so our exponent's a 2. Then we go down to 2s. Well, we have 2 electrons, so our exponent's a 2. We go across and we hit 2p, and again, I'm going to stop at 2 because that's where carbon's located. It only has 2 electrons in there. So the electron configuration really represents that. Let me try fluorine for you. Fluorine has 9 electrons. Okay, So it's a little further down than carbon. So we have to go further. So again, 1s2, 2s2, but then we're in 2p, and we don't stop at 2. We go 1, 2, 3, 4, 5. So my exponent is a 5. Something important to note here is your exponents should add up to the total number of electrons in the atom. So 2 plus 2 plus 5 gives us 9. Try magnesium and argon on your own time and check the key online to see if you did it right. Okay, electron configurations. Sometimes I'll give you the configuration and you have to tell me the element it represents. To do this, it's very easy. Just look at the last one, 3d3. Well, I know that this is 3d. 1, 2, 3 tells me it's vanadium. For the second example, 4d. Well, then this must be 4d. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's silver. Okay, and then the last one, 3p6. Here is 3p, and 6 is the last one, argon. So those are very, very easy to do. You just have to look at that very last energy level with the sublevel and the exponent.